In this video, I'm going to demonstrate how to test and measure the damper in the ESCO strut on a Lancer. To do this, we need to put the airplane up on jacks, and we're going to depressurize the nose strut, as you can see right here. I'm removing the nitrogen. When that is done, we're going to compress the strut, and the wood blocks are to temporarily hold it to make sure gravity doesn't just pull it back down. And by placing the Schrader valve cap back on, that will also help prevent gravity from pulling the strut back down. Now we're going to be using a tow bar to apply a torque to the strut. We're going to be applying exactly 20 foot-pounds. So I'm going to mark off the 2-foot location on the tow bar. And we'll be using a fish scale to apply 10 pounds to that 2-foot mark. But before doing that, I'm just checking the strut for any dead band. And the dead band is when you have a direction reversal, you don't want to feel any hesitation in the resistance of the strut. If there is, you either have air in the damper that needs to be worked out, or there's excessive play in some of the components inside the strut. So here I'm applying my 10 pounds at the 2-foot mark to get 20 foot-pounds of torque. And when you do this, you need to record the time, because what you want to do is go from full left to full right, or full right to full left, and record the time. We're going to be using that in a calculation here in a second. So here I'm going left to right. When you have those times, you'll simply multiply it by 12.3, and that will give you the damping value in units of foot-pounds seconds per radian. And we're going to compare that to some results here in a second. First, I'm going to recharge the strut with nitrogen. And on that 360, a good starting point is 200 psi. Should be a little bit more than you need. And to fine tune that, you put the airplane back on the ground, and you can easily remove some nitrogen just by tapping on the valve or the valve stem. What we have here is a chart that shows nominal damping values for the ESCO strut. You'll notice that it's very much a function of temperature. And this is due to the fact that the oil viscosity goes up as it gets colder. So when you take these damping measurements, you need to note what the temperature of the strut was at the time. If the aircraft has not flown recently, it's safe to assume that it's very, very close to ambient temperature. If the aircraft has flown recently, it's probably quite a bit warmer, so you'll need to measure it directly. The blue dot on that chart, those are the results from the measurements I just took earlier. Using the times recorded times the 12.3 came out to 147 foot-pound seconds per radian. That result is above the green line, so that is in good shape.
And finally, I wanted to address the min and max curves on this chart. Both are based on empirical data. Let's start with the maximum curve first. The upper bound of damping is really defined by the ability to steer the airplane. In other words, the damping will fight the steering input of the pilot. Struts that are above the nominal line, but bounded by the dash line, are known not to have any operational issues with steering. That doesn't mean this dash line is the absolute maximum, but within that region, no issues have been reported. The lower dashed line represents a loosely defined boundary between struts that have not had any shimmy events and those that have had a history of shimmy events. I would look at that as a caution line that you want to stay north of.